Hello and welcome to the fourth of a series of webinars on boundary systems organised by the Ocean Observations Physics and Climate Panel. My name's Colette Kerry and I'm going to talk about the East Australian Current System. This talk is the second of two talks on the East Australian Current. The first was given by my colleague Moninya Roughan on the observing system, and I'm going to talk about the modelling component and in particular how we have been using models to provide information on improving observing system design. I'm going to give an introduction to the EAC system, talk about the important processes and limitations of modelling those processes, the use of observations in models, and also how we are using models to look at observation impact and to improve observing system design, then give some suggestions for further observations based on these studies and some suggestions for advances in modelling and DA techniques. So the East Australian Current is the western boundary current of the South Pacific subtropical gyre. It flows poleward along the southeastern coast of Australia and typically separates from the coast around 32 south, shedding large anticyclonic and cyclonic eddies into the Tasman Sea. About 1/3 of the current transport continues southward towards Tasmania, and about 2/3 continues eastward as an eddy train towards the northern tip of New Zealand. In the mean field, the mean sea surface height of the East Australian Current looks like this, where we have the EAC typically separating around 32 south with some return flow. And this histogram shows the percentage of time at which the EAC separates from the coast. You can see that it typically does so between around 32 and 34 south, but the EAC can separate at any given latitude poleward of around 27 south, which is the latitude at which the EAC jet is typically most coherent. These snapshots on the right show sea surface temperature and sea surface height at three given times. And indicative of a typical state of the East Australian Current, which is characterised by these large anticyclonic and cyclonic eddies in the Tasman Sea. So we've learned a lot about the East Australian Current from observations and also more recently from long-term high-resolution model simulation. In this simulation, we've learnt that mesoscale sea surface height variability stems from both intrinsic instabilities of the EAC jet, which can be shown by this alongshore propagating mode in the sea surface height variability, as well as westward propagating Rossby waves, just shown by this second westward propagating mode. We've also shown using composite analysis that upstream transport controls separation latitude and penetration of the EAC to the south with a weaker, more stable EAC penetrating further poleward, resulting in higher heat content in the EAC southern extension region, whereas a stronger EAC separates further north, resulting in higher EKE in the Tasman Sea and a lower heat content in the southern extension region. In terms of long-term trends, we've seen that the EAC is weakening upstream of the typical separation region and strengthening poleward of the typical separation region, consistent with the poleward shift of the system, which strengthens as it evolves poleward. We understand a little bit about the vertical structure of eddies. This figure here shows the vertical structure of around 200 anticyclonic on the left and cyclonic on the right eddies from a free-running simulation. But what we don't understand so well is our ability to predict this vertical structure of eddies when we include data assimilation in our models. Some more complex vertical processes include the subduction and coalescence of eddies and also the subduction of coastal water masses beneath eddies, which we've observed, and we are working on our ability to model and predict these processes. So in summary, important processes and model limitations, some important processes in terms of prediction of the EAC and its separation from the coast include the strength and structure of the EAC jet upstream of separation, the separation of the EAC from the coast, eddy structure and evolution of the eddy field, the vorticity gradient inshore of the EAC, which has been shown to influence the growth of fine scale features, and also the westward propagating Rossby waves. And in terms of developing models, some of the considerations include horizontal and vertical resolution and data assimilation, particularly the assimilation of observations that provide us with information about these processes and effective data assimilation techniques that allow this information to effectively inform the models and therefore improve prediction. So in terms of the current use of observations in models, in Australia, we have a global ocean forecast system, which is a collaborative effort between the CSIRO and the Bureau of Meteorology. The current version uses a multi-scale or two-step data assimilation scheme, which provides improvement based on the previous scheme, and it assimilates a long track sea surface height, satellite sea surface temperature and Argo profiles, and CTD and XBT lines. And for verification, they're using drifting buoy SST, drifting buoy Eulerian currents, and sound speed profiles from Argo. So using these sound speed profiles to look at the depth of the deep sound channel, which is the approximate depth of the permanent thermocline. The newer multi-scale two-step data assimilation system gives improved representation in the South Equatorial Current region and also in the Gulf Stream and Kuroshio extension regions. Moving down to the scale of the EAC system, we've developed a high resolution regional model, which is nested inside this global model developed by the BOM and CSIRO. This regional nested model has a horizontal resolution that varies in the cross-shore direction with a resolution of 2.5 kilometers over the continental shelf and slope, up to 6 kilometers offshore, with a smoothing, with emphasis on maintaining shelf width, which is thought to be key to EAC separation. And we've conducted a series of experiments where we use four-dimensional variational data assimilation to assimilate a number of novel observations that were collected through Australia's integrated marine observing system. And these include, firstly, the more traditional observations, such as satellite drive sea surface height and sea surface temperature, Argo floats and XBTs, but also temperature and salinity from shelf moorings, temperature, salinity and velocities from a full depth mooring array off of 28 South, which is where the EAC is typically most coherent, a number of gliders which sample temperature and salinity on the continental shelf, as well as into eddies off of Sydney, and then a high frequency radar array which measures surface radial current speeds at around 30 degrees south up to about 100 kilometers offshore. So this assimilation system provides a good representation of the sea surface height, improved in the Tasman Sea region compared to the global simulation in which it is nested, with mean RMS sea surface height error of around 6 centimeters over the model domain, and sea surface temperature RMS error of around 0.4 degrees Celsius in the analysis. These plots show the root mean squared difference between the analysis and the observations in the magenta, the and free run in the observations in the blue, and then the observation anomaly in the black for potential density as measured by Argo floats, and then as measured by independent CTD cast observations. And we can see that are getting similar error reduction in the analysis for the non-assimilated observations as we are for the assimilated Argo floats, which provides confidence that the assimilation system is reducing uncertainty across the model domain. For surface velocities, these are the complex correlations under the HF radar footprint for the free run and the analysis. An example of the simulation of the HF radars for a specific case is shown here. So we can see that in the forecast, we have a southward flowing EAC with no recirculation inshore of the EAC. In the observations, there's indeed this cyclonic eddy under the HF radar footprint, which is then resolved in the analysis and manifests itself in the sea surface height field as well. And we'll see later that the impact of these HF radar observations is indeed far-reaching, both up and downstream. So we can use the 40 VAR data assimilation system to understand observation impact directly using the adjoint of the assimilation procedure, which is saved out when we perform the 40 VAR. So this is an example showing the number of observations per 5-day assimilation window, and then the impact of each observation platform on estimates of transport offshore of Sydney. So the transport difference is the difference between the forecast and the analysis transport. And we can see that the EAC array, which is the dark red, has a significant impact at some times, as does the HF radar, which is the green. And the glider observations off of Sydney have a significant impact as well when they are sampling the eddies off Sydney. So when we looked at these observations impacts, we looked at 5 different circulation metrics, looked at longshore transport through 4 different cross sections from at 28 south, 30 south, 34 south, and then into the EAC southern extension at 36 south, and then spatially average eddy kinetic energy in this region of high EKE. If we group the observations by latitude, this is the summed impact and then the impact per observation. We can see that the impact per observation of the satellite observations is greater in the region of high eddy kinetic energy, so between around 32 and 37 south. And similarly, grouping the observations per depth, again, the top panels show the summed impact and the bottom panels the impact per observation. We see that the impact per observation is greatest in the upper 400 meters, and the gliders, both on the shelf and in the eddies offshore of Sydney, have a considerable impact on estimates of EKE as well as transport through 28 south and 34 south. If we average the observation impact over the 2-year period for which the assimilation was run, we can see that the impact of the HF radar on transport through the 4 sections is disproportionately large compared to the number of observations. The HF radar observations impact the vorticity inshore of the East Australian current. This plot here shows the vorticity difference between the analysis and the forecast. We can see that in the analysis, we have increased cyclonic vorticity inshore of the EAC. The difference in vorticity between an assimilation that assimilates the HF radars and assimilates only the traditional observations also shows an increase in cyclonic vorticity inshore of the EAC, as well as an increase in vorticity standard deviation. For the gliders, they have impacts on average between about 6 and 12% over the 2-year period. But if we average over only the period for which they sample eddies offshore of Sydney, the impacts are much more significant, between about 28 and 36 south on transport estimates through the 4 sections and 38% on EKE. This is because the gliders provide detailed information on the depth structure of the eddies, which can be seen in this comparison here, where the top panels show an eddy in the assimilation system that only assimilates traditional observations, and the eddy is quite deep. But when the eddy is constrained by a glider, the eddy depth is much more realistic. So in summary, these observation impact experiments have allowed us to make suggestions for further observations. The experiment showed that observations taken in regions with greater natural variability are most impactful. Sea surface height and sea surface temperature observations between 32 and 37 south have more impact on transport estimates along the coast than the same observations taken elsewhere. And observations in the upper 400 meters are more impactful as they reveal information about the structure of the mixed layer and the thermocline. Deep gliders deployed in EAC eddies are particularly impactful, and observation impact is far-reaching up and downstream and forward and backward in time, specifically the observations from the HF radar and the EAC array. In the global system, comparisons between an ensemble Kalman filter data assimilation system and ensemble optimal interpolation showed that ENKF begins to make the same magnitude of correction at depths below 500 meters, and indicating that the constraint from altimetry becomes insufficient below 500 meters. So in light of this, we might suggest targeting Argo floats or piloting Argo floats into eddies to better represent these, the depth of eddies in light of the 40 VAR experiments, which showed the importance of the sustained mooring array. Given that the funding for the current mooring array is likely to end in 2023, we're interested in understanding whether we can pilot gliders across this section to get similar results as a sustained mooring array, which is significantly more expensive. We saw that the HF radar array had significant impact, and we now have a HF radar array further south in the more eddy-dominated region. And so we'll be looking in the future at the impact of this radar array, which measures the eddy field downstream rather than the more coherent EAC jet. So in terms of suggested observation simulation experiments, our focus is particularly on comparing, say, observations of the coherent jet upstream, which we understand drives downstream EAC separation and eddy kinetic energy, versus observing the downstream eddy field, which is indeed chaotic. And it's likely that we need observations of both to get an optimum data assimilation system and effective predictions. So our last point is suggestions for advances in modelling and DA techniques. And for our global system, the Bureau of Meteorology and CSIRO have developed an ensemble Kalman filter data assimilation system, which is showing significant improvements based on the previous ENOI system that they have been using. The forecast innovations are considerably lower, shown by the magenta, than the other systems. These plots show the sea level increments for the most recent ENOI system and then the ENKF system, and the increments are considerably lower. Likewise, the ensemble Kalman filter is showing lower background current magnitudes across the Tasman Sea at various depths, with well-defined and separated eddies and less kinetic energy at depth. And some comparisons for other boundary current systems represented in this global model. We can also see that there's improvement in the ENKF compared to the previous ENI system in both the Gulf Stream extension and the Kuroshio. So in terms of suggestions for advances in modelling and DA techniques, we saw that the ENKF in the global system provides considerable improvement compared to the ENOI. In terms of the 40 VAR experiments at a regional scale, we showed that surface vorticity inshore of the EAC and vorticity variance improved by assimilating the HF radar. EAC core depth from about 27 to 30 south was constrained by the EAC array, and eddy depth was constrained in the vicinity of the gliders. However, EAC core and eddies are too deep when not constrained with observations. We also found that when assimilating all available observations, including the novel observations, we got similar surface and subsurface predictive skill after 5 days than the system that assimilated only the traditional observations. So the DA of novel observations should provide better forecast still if the system is well tuned to represent EAC dynamics. And so our ongoing goal is that the impact of the novel observations be more far-reaching in time and space through improved specification of background error covariances. And in light of this, we're working on introducing balanced operators such that the background errors covary, and hoping that improved depth representation does in turn improve prediction of eddy shedding and eddy interactions. Downscaling to a high resolution model of 750 meter resolution, we found that we got improved estimates of cyclonic vorticity in shore of the EAC. However, the frontal eddies did not form or evolve with the correct timing or location in the forecast. And therefore, for rapidly evolving flow features, we must focus on reducing model error. And in particular, we're looking at parameter estimation in the 40-bar control vector to tune the model rather than use data assimilation. And recently, Peter Oak from CSIRO and myself chaired a working group as part of the joint ECM-WF Ocean Predict workshop. And some of the suggestions for advances in modelling and DA techniques that came out of that were, firstly, that time-dependent or 40-bar or ENKF techniques are required to exploit novel observations such as gliders, HF radar and SWAT, and move towards predicting more rapidly evolving processes. There was also a lot of talk about ocean atmosphere coupled DA, where flow-dependent covariance matrices are necessary in order to adapt relatively short coupled DA windows. And suggestions were to work towards hybrid methods where flow-dependent covariances were used in 40-bar using ensembles. And then for the higher resolution regional models, looking at parameter estimation versus data assimilation for better tuning of the models. So in summary, I've talked about the use of observations to inform models, but also how we've been using models in the EAC system to inform observing system design. So we've learned a lot about the EAC from both observations and numerical models. We've then assimilated a variety of observations into our numerical models, and understanding the impact of these observations is then able to feed back into the observing system design. So we're hoping that some of this work can motivate smarter observing systems and therefore move towards improved prediction and improved understanding of the important processes in the EAC. Thank you.